Good morning, everyone. Today we'll be discussing about rheology. What is rheology? The definition of rheology, the concept that we have already seen in our previous lecture. In today's lecture, we'll be discussing about the methods to determine the viscosity. What are the various methods that are used in the pharmaceutical field? And now, in this lecture, we'll be discussing about the different determination methods and type of instruments used to determine viscosity, applications of rheology in our pharmaceutical field. The thing you need to know is the instrument used to determine viscosity is known as viscometer. We're having different viscometers based on the nature of the liquid for which the viscosity is being determined. Now these are the various viscometers available. We have a specific classification. The first one is capillary viscometer. Second category, rising and falling body type of apparatus. The third category is rotational viscometer. And we'll be able to see all these examples. Now we'll be looking in detail of all these viscometers. Now, as we know, based on the type of flow, there are two different systems or two materials called Newtonian systems and non-Newtonian systems. As you all know, in Newtonian systems, if we increase the shear stress, the rate of shear increases, but there will be no change in the viscosity. Whereas for non-Newtonian systems, if you keep on increasing stress, then of course the viscosity of the fluid, of the material keeps changing with the stress that you have been applying. So those systems are known as non-Newtonian systems. As you all know, most of the pharmaceutical formulations, they fall under the category of non-Newtonian system. Means when you apply pressure, it will affect the viscosity. So now, based upon the materials of the different substances like Newtonian and non-Newtonian, we are having different instruments. Now we'll be seeing one by one in detail. The first one is capillary viscometer. The name itself indicates this instrument has a capillary column. Now, I will be explaining you with one example. For example, say you have taken a sample A and you have taken a sample B. Now, if a sample A takes 1 minute to flow from one point to another point, and if sample B takes 30 seconds to flow from one point to the other point, which of these samples would you say is having a greater viscosity? Obviously, the one which takes longer time to reach from one point to other point, right? Because it is showing some resistance towards the flow, right? So, based upon this time of flow, we will be able to determine the viscosity. That is a concept behind this working principle. Now let's see. So these are the equations by which we'll be discussing in future. Now, I'd like to explain first this one. The Oswald viscometer, it has two arms, the left arm and the right arm. In the left arm, you'll be able to see a bulb on this. Hello? We have two marks A and B above and below the bulb. On the other arm, we'll be seeing a bulb which acts like a reservoir with the mark C. Now, the sample of which we are supposed to determine viscosity is placed in the arm having the bulb C. With the help of pipette, we'll be pouring down the liquid through this arm. And from the other arm, which has marks A and B, from this arm, the liquid is sucked till the liquid reaches the level or the mark A. Now, close that arm with the help of thumb and then fix this viscometer to a stand with the help of a clamp. Now, remove the finger. The liquid tries to flow down from mark A to mark B. Now, the time taken for the liquid to flow from mark A and B is noted down. The similar procedure is carried out with the another liquid, a standard liquid like water, of which the surface tension, the viscosity is known. The known liquid is taken. The similar procedure is carried out with the liquid will be sucked inside the arm having two marks. The liquid will be reaching mark A and time taken for the liquid to flow from mark A to mark B is noted down. We need to know the density of two liquids, this liquid, the test liquid and the known liquid. As we all know, the density of the water is nearly 1. Density of the liquid can be determined by means of specific gravity model. So at the end of experiment, we'll be having different parameters like the time taken by the test liquid to flow and time taken by the water, the known liquid, to flow from mark A to mark B, the densities of the water and the density of the test sample. So by means of these parameters, we'll be able to determine the viscosity of the given test liquid. It is like a comparative study. We'll be comparing the test results with that of a standard result. We already have a standard viscosity value for water. Now we are having a special formula by which we'll be able to determine, be able to compare the results with that of a standard liquid. Now here the viscosity is denoted by eta, as you all know. We have an equation called eta 1 by eta 2 is equals to rho 1 T1 by rho 2 T2. Here the rho indicates the density. Let us consider eta the 1 as the test sample, eta 2 as the standard water, the standard liquid. In this experiment, we have taken standard liquid as water. We know already the viscosity of the standard one. So, this only eta 1 we need to find out. Eta 1 by the known value is equals to rho 1, the density of the test, time taken by the test liquid to flow, by the density of water into time taken by the water to flow. So by cross multiplication, eta 1 is equals to rho 1 T1 by rho 2 T2 into eta 2. So this equation is actually derived from a Poiseuille's equation, which is seen in previous slides. So in short, the viscosity of a liquid depends upon the density of the liquid and time taken for the flow. And the next method is falling and rising body apparatus. In this type of apparatus, The name itself indicates like we are having some body or a ball which falls or which raises. Now to get started with this type of apparatus, I would like to quote one example. For um, take a beaker with a sample A, drop down a metal ball. Now note down the time taken for a metal ball to reach the bottom of the beaker. For example, if the time taken for a ball to reach the bottom of the beaker is 1 minute. Now take another beaker, fill it with another sample. Now place the same metal ball. Note down the time taken for the ball to reach the bottom of the beaker. Now, if this ball takes 20 seconds to reach its bottom. Now tell me, out of these two cases, which sample do you think will be having greater viscosity? Of course, A. Because it is taking much time to reach the bottom, which indicates the fluid is showing some resistance towards the movement, right? So based upon the viscous drag or the resistance experienced by the metal ball during its movement indicates the viscosity of the given sample. This is the basic concept behind this apparatus, the working principle. Now let's see in detail what are the different ways apparatus are available under this category. The first one is the falling sphere viscometer. Example, Hopler ball viscometer. The second type of instrument is rising sphere. The name itself indicates in the first type, the metal ball will be falling down, and in the second one, we'll be seeing the rise of the ball or the sphere. Now, this second category, rising sphere viscometer, is also known as rheometer in few textbooks or the journals. Now, let's see what actually happens in this instrument, the falling sphere viscometer, how it really works. When we keep in consideration of the given example that was quoted before, now the working principle includes or it is based on Stokes' law. Hope you all remember Stokes' law. Stokes' law which we have discussed in our the rate of sedimentation. According to this law, you know, for a falling body, it should experience some resistance or viscous drag based on the type of solvent. If the solvent or the medium is too viscous, then the resistance will be even more, the viscous drag will be more. In short, the body or the metal ball will be experiencing more resistance to fall down. So, the viscous drag on the body is equals to force responsible for the downward movement, right? If it is having more viscous drag, more resistance means it is taking more time to reach the bottom of the beaker, and at the same time, it is responsible for the movement. So, this Stokes' law is given by an equation. Eta is equals to d square g into rho s minus rho 1 by 18v. Let's see what are the different parameters. Before that, let's see how our rising or how our falling body type of viscometer looks. This is the falling sphere viscometer. It will be having two, not the glass columns which are surrounded by a water jacket, and in this column will be filling with the sample, the test liquid, and the metal balls will be given in different sizes, and the metal by which the ball is made, all the information will be given in the manual. The density of the metal used in this manufacture is already given in the instructions manual of this segment. So our next step would be the filling of this column with the test liquid and then placing the ball on the top of this instrument. Let the ball fall down. So now we'll be noting down the time taken by the ball to reach the bottom. Similarly, we'll be carrying out the same procedure for unknown sample like water, because we already know the viscosity of the water. It is a standard value. We need to know the time taken for the ball to reach from the surface to the bottom of this column. Now, as we are having that equation, we need to incorporate all the values which we get from this experiment, like the diameter of the sphere that we can check by means of vernier calipers, acceleration due to gravity is constant, density of the sphere can be obtained from the instructions manual, density of the liquid can be determined by means of your specific gravity bottle method, and terminal velocity. Now here comes. Now here we need to make sure the time taken for the sphere to fall from 2 points. When you look clearly, I'll be having 2 marks, just like in the previous viscometer. We'll be having 2 marks. The time taken for a ball to move from one point to the other is noted down. How can we determine velocity from this parameter? It's so simple. The velocity is given by the ratio of the distance traveled to the time taken. Now the distance between these 2 marks divided by the time taken by the ball to reach. So from that we'll be able to determine the terminal velocity. So by incorporating all these values in the above equation, we'll be able to see that. So if we clearly see this one, it looks like this. We'll be having the column which is surrounded by a water jacket, which has 2 marks A and B. The time taken by the metal ball to reach B from A is noted down. Distance between A and B is constant, so that this distance by the time divided by time gives the terminal velocity. Now, for every instrument there will be some errors. So to avoid the errors, we need to multiply the observed value, by a correction factor which is constant for specific instruments. So, and in which we get the viscosity into correction factor, our corrected viscosity. For more details, you can watch the video which is in this link for your better understanding. Rotational viscometers are the instruments used to check or determine the viscosity of non-Newtonian systems. Non-Newtonian systems are the systems in which there will be a change in the viscosity when we change the shear stress. If we increase or decrease the shear stress, it is going to affect the viscosity of the materials. Such kind of materials are known as non-Newtonian materials, and most of the pharmaceutical formulations, they come under this category. So in short, rotational viscometers are the instruments that are used to check the viscosity of pharmaceutical dosage forms. These are categorized into two different types: cup and bob viscometer, cone and plate viscometer. So the name itself, indicates this instrument has one part which shows rotations. Now let's see in detail about each type, the cup and bob viscometer. The name itself indicates that this instrument has two parts, the cup and the bob. These both are arranged coaxially, and the outer cylinder, it forms a cup, and the inner cylinder, it is known as bob. It is fixed centrally. And in this kind of instrument, in cup and bob kind of instruments, either of these parts will be stationary. It could be your cup. If cup is stationary, the bob keeps rotating, and if bob is kept stationary, the cup will be rotating. Based on these two variations, our viscometer is classified as Couth type and serial type. Couth type of instrument is where the cup will be under rotation and the bob will be stationary. And serial type, the bob will be rotating and the cup will be stationary. Now for better understanding, if we see the picture, we'll be having a better idea. Now see, we are having two type of cup and bob viscometers. Couth type, where cup is rotated and the bob will be stationary, and when it rotates, we'll be placing our sample between the cup and the bob. When the cup rotates, there will be some resistance offered onto the surface of the bob. Now this resistance, or the viscous drag on the bob, that actually causes some torque or force on the bob. Now this force experienced by the bob because of the viscous drag is directly proportional to the viscosity of the fluid, of the sample. In short, if it is more viscous, if the sample has greater viscosity, the greater is the force acted upon the bob surface. That can be easily read on a digital meter which is present in the instrument. Now for such kind of Couth type of cup and bob viscometers comes our Michael viscometer. And the next type is serial type. The bob will be under rotation and the cup would be stationary. And the examples are Stromer's viscometer, Brookfield viscometer. These are the two viscometers that come under this category. In most of the pharmaceutical industries, for determining the viscosity of all the various dosage forms, this is the type of viscometers majorly used, like the Brookfield viscometer especially. Now let's see in detail how these viscometers actually work. What is the construction, how it works, that we'll see now. First, we'll look at the Couth type, where the cup is rotated. Now here you are seeing a working principle diagram of a Couth type viscometer where the cup is rotated. See, you are able to see a revolving outer cylinder which is fixed to a motor, and inside that we are seeing a cylinder which acts like a bob that is fixed or attached to a wire, a tension wire or torsion wire. Now, the sample is placed between the bob and the cup, between the inner cylinder and the revolving outer cylinder. Now, if the cup rotates, what happens to the sample? The sample keeps on rotating, and if it is too viscous, during this movement, there'll be some force acting on the bob, because if the sample is too viscous, it causes some force, some resistance. That resistance or the viscous drag will be experienced on the surface of the bob. Now, this is easily read as torsion. There's nothing but the force acted upon the bob that can be easily seen. So, here the thing is, we are actually, we can even change the speed of the cup. Means here we can change the rate of shear, right? And the torque or the torsion experienced by the bob would be our rate of shear. So that's how, here we are able to see the shear stress and the rate of shear. Rate of shear here will be from your revolving outer cylinder, and the stress will be experienced by the bob. As you all know, viscosity is equals to eta is equals to shear stress by rate of shear. So that is how we can actually know the viscosity of the given sample. The rate of shear is the number of rotations, the cup speed. The shear stress is the force that is experienced by the bob. That's how we can determine the viscosity of the given sample by this code type viscometer. And next is the serial type viscometer. Here the bob rotates and the cup is stationary. Most of the rheological properties of non-Newtonian systems are better explained or better determined by these kind of viscometers. So let's discuss in detail with the help of diagram. Now this is your Stromer viscometer. The cup is stationary, but the bob keeps moving. Now when we look at this instrument, we will be able to see the cup here is your sample holder. We have taken some sample in a beaker. So that is your cup with the sample. And you're able to see a metallic rod from the instrument that acts as a bob. It actually rotates. Now, let's see how this viscometer works. Now this instrument is having another holder over which we can put on weights. We'll see how this holder actually plays a role in determining the viscosity. Now take a beaker with a sample and place on the instrument. So the bob will be inside the beaker. Now, slowly the weight is placed on the holder or the hanger, and you need to set the instrument to a specific number of rotations, and we need to check for the time taken for the bob to undergo that particular number of rotations. For example, if we have taken a sample, now I have added some weight onto the hanger, and I have checked and I have set the instrument to a specific speed of say 100 rpm. means it rotates 100 rotations per minute, right? I've said that. Now just run the instrument. Now we'll be checking for how much time, I mean for that particular minute, for 1 minute, how many rotations your bob is going to make. We'll be noting down. Now we'll be keep on increasing, we'll be keep on increasing the weights on the hanger, and then again we'll be checking for the number of rotations made by the bob. The interesting thing is there will be some change. As you keep on increasing the weights, we are actually pressurizing the system. We are increasing the stress on the system. And that is actually affecting the rotations of the bob. Here, the weights are increased gradually. Now that represents your shear stress. You're increasing the shear stress and you're checking for the rate of shear. Rate of shear here represents the number of rotations. Now during this rotation, because of this rotation, there will be some changes, molecular changes that happen in the sample. Thus, that changes can be easily read because because of these rotations, if this liquid turns out to be more viscous, if it undergoes some changes in the viscosity, the bob will not make the same number of rotations. Because of the increased viscosity, there will be some resistance in the rotation and there will be some decrease in the number of rotations per minute. So when we change the weights on the hanger, there will be some change in the number of rotations. Why? Because there's been some change in the viscosity of the sample that is taken in a beaker. So by relating all these parameters, a rheogram is plotted. Rheogram is nothing but a graph that is plotted between the weight added on your x-axis and RPM on your y-axis. Nothing but the shear stress on the x-axis and the rate of shear on the y-axis. So like that, this is how we can actually get the rate of shear and the shear stress from this kind of instrument. And this is the equation by which the viscosity can be easily calculated. Viscosity eta is equals to kV W by V. kV is the instrument constant to avoid errors, and W is the weights added, and V is the number of rotations made by the bob. And if we use any materials which show plastic flow, we don't know, which might show some plastic flow properties, and if if we want to detect the plastic flow properties of a given material, we don't know whether it is a plastic, whether it shows a plastic flow or a pseudoplastic flow or a dilatant flow. But still we have another formula. Plastic viscosity U is equals to kV into W minus WF by V. This is the same plastic viscosity in the equation. But here, as we have considered the weights added to be our shear stress, we'll be considering W as our shear stress. WF is the yield value that can be easily obtained from the graph by extrapolating the point towards the x-axis. Next one is the Brookfield viscometer. This is the most sensitive instrument that's used in the pharmaceutical company to determine the viscosity. Majorly, this is the instrument which is used to determine the viscosity of uh, ointments, gels, uh, thick suspensions, concentrated suspensions, semi-solids. Now let's see in detail. When you look at the picture, you'll be able to see a rotating bulb, a monitor, right? It is just like your code type, but here, in this, the bulb will be keep on rotating, will be placing the beaker, just like your Stromer viscometer. But when compared to Stromer, this is more sensitive. And it has a monitor too. The number of rotations made by the bulb will be easily seen, and the force experienced on the bulb will be seen on the monitor. And it is completely automatic. We can easily get the viscosity from the monitor itself. That's why this is most commonly used in the pharmaceutical field. It is fully automated, and the error correction and the error will be much lesser because it produces the results by considering the error factor also. Now let's see what are the disadvantages. The distance between the cup and the bulb should not be large. It should be very less, because the shear stress when a bulb rotates should be experienced by the whole sample. If the gap between the cup and bulb is more, we cannot actually make sure that all the sample, every part of the sample will be having the same shearing stress. And again, we need to have large amounts of sample to be analyzed for its viscosity. You might have seen in your picture, you have taken in a beaker, at least half to 3/4 quantities of the beaker is filled with the sample. And during this process of rotation of either cup or the bulb, there might be chances of production of heat, and this temperature increase can affect the viscosity. So there are few chances of getting false results. To avoid that, our cup or the instrument should be surrounded by a water jacket where the temperature is completely controlled. So that is how we need to actually consider all these factors when we are choosing the equipment for the determination of viscosity. Next one is the cone and plate viscometer. The name itself indicates in this instrument we'll be having either cone and plate. Just like the cup and the bulb viscometer, here we'll be having a cone and a plate. The most advantageous part is for this kind of instruments will be not using much sample. It's just small quantities will be enough. And how this actually works is given in the link below. You can get the details of how it actually works. So when you look at the picture, you're able to see a cone shaped part and a horizontal plate like part. It is a flat circular plate with a wide angle cone placed centrally on it. During operation, the sample is placed at the center of the plate, and slowly it is raised so that the tip of the cone and the plate touches. Now this cone is attached to a motor which helps the cone to rotate with variable speed. When it rotates, the sample will experience some rate of shear as it is placed between the rotating cone and the stationary plate. Now, the rate of shear is actually can be altered. It can be either increased or decreased. Rate of shear here it is expressed in the revolutions per minute. And because of these rotations, there is some torque produced on the cone, and that is measured. It can be easily get by the meter that is attached to it. Now, we need to plot a rheogram by taking shear stress on x-axis and rate of shear on y-axis. Do always remember, rate of shear is always explained or expressed as RPM, rotations per minute or revolutions per minute. That can be easily read from the scale or the monitor of the instrument. Right? So the only simple thing is like we'll be calculating the rate of shear with shear stress. Right? Do always remember rate of shear is expressed in terms of RPM and shear stress is expressed as a torque experienced or the stress experienced. Of this kind of cone and plate, our Ferranti-Shirley viscometer is categorized as a cone and plate viscometer. Now this is, by this formula will be determining the viscosity. Viscosity is equals to C into T by V. C, instrument constant into torque reading by the speed of cone. Now for a plastic flow, this equation is slightly modified as plastic viscosity U is equals to C into T minus TF by V, where TF is the shearing stress that is experienced at the yield point. So the yield value is obtained by multiplying the TF by instrumental constant. This is how we'll be obtaining yield value. Now let's see the advantages of cone and plate over cup and warp. The most important advantage is the quantity of the sample. We need only little amount of sample to be analyzed in cone and plate viscometer. And the cleaning and filling of this equipment is much easier. Till now we have seen the different instruments used to determine the viscosity. Now we'll be looking on a concept known as viscoelasticity. The name itself indicates this phenomena comprises both the viscous nature and elastic nature. A viscoelasticity is the property of materials which exhibit both the viscous nature and the elastic nature of the solids. Now, most of the body fluids, biological fluids and semi-solids of pharmaceutical field, they exhibit this kind of phenomena. They exist as both liquids and solids. The viscous nature of the liquid, the elastic nature of the solids. Based on how much stress we are applying on it, the nature of the material changes. The viscoelasticity can be determined by a viscometer known as creep viscometer. For the special case The speciality of these materials is when they are subjected to stress for a shorter period of time, they undergo slight deformation. And that deformation is only seen under the influence of stress. But when once the stress is removed, they exhibit their elastic behavior by returning to their original shape with a slight deformation. And that slight deformation would be a permanent deformation. Now let's see what are the various applications of rheology in pharmacy. The important factor why we need to study this phenomena is to know the nature of the formulation under stress conditions. For example, if we shake a suspension bottle, because of this shaking, we are actually stressing up the formulation. We are actually pressurizing the formulation, applying more stress, shear stress on the formulation. And how the formulation behaves, whether it gets diluted, whether it gets less viscous, or whether it gets a gel form, would be our rate of shear. And because of these changes, it is actually necessary for a pharmacist to know how we can pack, what are the criteria to be considered when we pack a particular formulation. For such kind, let's see the rheological behavior of few pharmaceutical dosage forms. Let's see first emulsions. Under emulsions, we have different categories like lotions, creams, diluted lotions, creams, cosmetic creams. They show different behavior under stress conditions. If you could see, so for example, let's consider the creams. They are thick in the container, right? When we take some amount of cream and when we apply over the skin, do you think the viscosity of the cream remains constant? No. The viscous nature of the cream will change. When you are applying cream, means you're applying some shear stress on the cream at the molecular level. When you're rubbing it, you're actually creating some shear stress. And the cream, the viscous nature of the cream gets lessened and it gets easily applied on the skin as a thin film. The viscous nature is getting reduced. Hence, this kind of system is known as a shear thinning system. Shear thinning phenomenon. When you're applying shear, some thinning or decrease in the viscosity is seen. So, this phenomenon is known as shear thinning phenomena. Likewise, if we see the rheological behavior of a pharmaceutical formulation, you can see it. Similarly, the changes or the behavioral changes of ointments and gels can be easily seen when they are applied. Some stress. And for powders, for the flow property of a powder, it is considered as the rheological behavior of powder. The surface characteristics of particles play a major role in determining the flow property or the rheological behavior of a particulate solid. The most important point, the part is how this concept of rheology is applicable in the industry, especially the pharmaceutical industry. In the pharmaceutical industry, in the part of mixing of all the ingredients, this phenomena plays a major role. All the mixer or blender will be having large impellers which are under rotation. Now here large impeller is like the bob, the rotating bob, which we have seen in the cup and bob type of viscometers. When these impellers are run at very high shear rate, it actually changes the viscous nature of the material. It could either increase the viscosity or it could either decrease the viscosity based upon the nature of the material. So it is always better to run the mixer or to run the impeller at very low shear rate. Always make sure it should be at low shear rate. The mixing should be done. And again, the most important case is like when we are mixing some polymeric solutions or polymeric dispersions, if we run the mixing unit at higher speed, higher shear rate, there is a chance for these polymers to undergo breakdown at the molecular level because of the shear. So this actually results in the structure breakdown. So your polymer will no more be a polymer, it will be like a dimers or monomers, and the physical structure or the nature of the polymer will be lost. And it is nothing but it leads to depolymerization at high shear rates. So it is really very important actually maintain low shear rates, and also during the fluid transfers from one unit to another unit. So these are the different areas in the pharmaceutical field where the rheology plays a major role. So these are impellers of different sizes and shapes. So when you look at this figure, you're able to see different impellers seen in the mixing equipment. So this is just like a rotating bob on the cup, the rotating impeller and the vessel. If the distance is more, now the shear stress experienced by all the particles will not be uniform. And if the bob or the impeller is run at higher speed, it creates some turbulence and it affects the viscosity. So this is how the rheological behavior of materials play a major role